Limiting reactant stoichiometry. Often when we are carrying out a reaction, the reactants themselves are not mixed in their perfect stoichiometric amounts, meaning that if they're reacting in a 1-to-1 ratio, you don't always get them in a 1-to-1 ratio. Often more than one of them, and again, it depends on how many reactants you have, but let's say you have 2 reactants, then one of them you'll have in excess. So you have more of it than will be used in the reaction, and then that means that the other one is going to get completely used up. So they are not in the perfect molar ratios that is dictated by the reaction itself, and therefore one's going to run out before the other. The one that runs out is referred to as the limiting reactant. It limits the amount of product that's going to be produced. So when you're given a question that has more than just one amount of reactant given to you, so if they say, oh, reactant A, you've got this much, reactant B, you've got that much, you don't know which one's going to run out first. You don't know which one is the limiting reactant. And so you kind of have to find out which one of these things is going to be the limiting reactant, because whichever one runs out first will dictate how much product you actually get, because it's going to run out before you can make any more than that. So the limiting reactant is the reactant that produces the least amount of product. So you look at your reactants and you look at which one will produce the least amount of product. That is the limiting reactant. Notice it is not the one you have the least of. That's a different matter, because the amounts that you have them in may not limit how much you can produce. Just because you have less of one doesn't mean it's the one that's going to run out, because how they're used in the reaction, one of them might be used more. You might be using one 5 times as much as you're using the other. So even you have less of one, it might not be the limiting reactant. The limiting reactant is the reactant that produces the least amount of product. So the question is, how do you figure that out? So let's try it here. And a couple of ways of doing this. I'm going to show you my favorite way of doing it. The other way of doing it is to take the amounts of your reactants. You'll notice here we've got 2 reactants, aluminum iodine, and we've got 2 amounts of these reactants. So we can't just do one set of calculation. We're going to have to do more than one set of calculation. So one way to do it is to say, okay, let's find out how many moles of each one of these we have. We know from the equation here they're in a 1-to-1 ratio. So if we can find out how many moles of aluminum we have and find out how many moles of iodine we have, we could then say, okay, which one do we have the least of? And since they're in a 1-to-1 ratio, then that one would run out first. So we find out how many moles there are and find out how much they're being used, and that can be done to find which one's limiting. That's a way of doing it. The way that I'm going to show you doing it is that we're actually going to translate that all the way to product. It's not that hard to do. It's a little bit of extra work, but often you have to do that work anyways to get the answer to the question. So we're going to actually find out how much product you can make from both of these, knowing full well that one of them we will not be able to make that amount of product. So we won't use that answer. We'll find out which one produces the least amount of product. That will be the limiting, and that will be the answer we're going to go with. So first thing, as with all stoichiometry, we have to balance the equation. So get the equation, make sure it is balanced, and you can put the states in there as well. Aluminum solid, iodine, we'd have as a solid probably here, or iodine gas, and then aluminum iodide would be our ionic solid. Then we want to do the work to find the limiting reactant. So essentially, we're going to do 2 sets of calculation. We're going to take the aluminum, and we're going to find out how much product we can make. And then we're going to take the iodine and find out how much product we can make. That'll obviously give us 2 different answers, probably, unless they're in perfect stoichiometric amounts. But otherwise, we'll get 2 different answers. And whichever one produces the least amount of product, that one's the limiting reactant. So we'll convert both of these to moles. We're going to use the mole ratio from the equation, and then we'll actually, we could stop with the moles of product, but we'll actually go right to the mass of the product, often because the question's normally asking about mass anyways, and it's the same conversion factor, so once we do it once, it'll be easy to do it again. So the reactant that produces the least amount of product is the limiting reactant. That's the key there. It's not necessarily the one that there's the least of, it is the one that produces the least amount of product. So we'll find out how much product both of them can make. Whichever one produces the least amount of product, that's the limiting reactant. We'll actually cross off the other amount because that's not a real amount. You can't actually make that much because the other reactant will run out before we can make that. Let's see what that looks like. So for aluminum, it's one of the reactants. It might be limiting. We got to find out. We're going to find out how much product we can make. So this is just the same stoichiometry we've been doing. We're going to take the mass given to us. We're going to then convert it to moles using the molar mass. And again, it's per mole. And so we're using 1 mole. We look at the mole ratio from the equation, and the mole ratio between the aluminum and the aluminum iodide. Times New Roman's better. And so that is a 2-to-2 ratio. This then can be converted to mass of aluminum iodide by using the molar mass of aluminum iodide. 1 aluminum, 3 iodines gives you a molar mass of 407.68-ish. And so the amount of product that we could make if we used all of this aluminum and we turned it all into aluminum iodide, we could get 18.1 grams of aluminum iodide. But the problem is, we also have an amount, we don't have excess iodine. So you'll notice some of the non-limiting reactant stoichiometry questions would say you have excess other reactant. The other reactant here is iodine, and we don't have excess, we have a specific amount. So we've got to use that specific amount and find out, okay, well, the aluminum could maybe make 18 grams of product, 18.1 grams of product. How much could iodine do? And again, that's just normal stoichiometry. We take the mass of the iodine and we use its molar mass, 1 mole of iodine. And remember, we say iodine, we're talking about it being diatomic, I2. So its molar mass is, there's 2 of them there, so we have to add iodine once and again twice. And so the molar mass of iodine, molecules of iodine, I2, is 235.8. There are 2 iodines per molecule. We use the molar mass that would convert from iodine to aluminum iodide. And then notice this is why it's not that hard to go to mass for both of them, because this last conversion factor is the same one. We've already calculated the molar mass, so we can just reuse that calculation. And we plug in our numbers and we get 2.57. So if we used up all of our iodine, we would get 2.57 grams of product. Now here's the problem, right? We've got 2 answers here. If we used all of our aluminum, we could make 18. If we used up all our iodine, we could make like 2.8, 2.57, let's say. So the above answer here, the aluminum, this 18.1 grams is not a real answer, because in order to do that, you'd have to have more iodine. Because we know if we used up all of our iodine, we would only get 2.57 grams of it. So this is the correct answer. This tells us the iodine is limiting. The aluminum is the one that doesn't run out. It's not limiting. It is the excess reactant. It is the one that is not going to run out. The iodine is the one that is going to run out. It is the one that is limiting. And we can tell that because we compare the amount of products that each one can make, and we can see I got my pen back, I think. Okay, there we go. So we can compare these two, and we see that 18 is larger than 2.57. Therefore, 18 is not the real answer. That is not how much you can actually make as a product. The one that produces the least amount of product, that is the limiting reactant, and that is the amount of product you can actually produce. Cross off the other one because it is not a real number. You can't make that much because you'd run out of iodine before you could. So then we can say, therefore, iodine is limiting. 2.57 grams of aluminum iodide is produced. Make sure you do cross off that other one, because another popular question to ask is, how much excess reaction would be left over? Another way of saying that would be, okay, we're not going to use all our aluminum, so how much would we have left over? Make sure you do not use the amount of product made from that aluminum, because you can't actually make that amount of product. You'd run out of iodine before that happened. So to do that separate set, let's try it out. Determining the amount of excess reactant left over. Exact same question as before. We've got the same reaction, but we're asking in a slightly different way. We're saying not which one's going to be limiting, not how much product's going to be produced, but we know that between the aluminum and the iodine, one of them runs out first, and you know the answer is the iodine, and one of them is excess. We know from before that it's aluminum that's excess. So how much of that excess will be left over? We're going to use some of it, not all of it. How much of it will be left over? So to do this, again, we'll do the exact same thing, and I'm going to fly through this because it's this exact same part we just did. We can find the amount of product made from aluminum, the amount of product made from iodine, and we know that iodine is the limiting reactant. We only get 2.57 grams of aluminum. So that part's the same as what we did before. Be sure to cross off the other answers so you're not tempted to use it, because the question's asking for, okay, how much aluminum, the excess reactant, how much of it's left over? There is 1.2 grams that we started with. So the question really is, well, if we start with 1.2 and we use some amount, how much did we use? If we can find out how much we used and we subtract it from the amount that we started with, we have our answer. To find out how much aluminum is actually used, we can either use the limiting reactants amount, Get rid of that. The limiting reactants amount of 2.4 grams, because that does actually go through the reaction. We could use the amount of product produced from the limiting reactant, because that is the amount that is also produced during the reaction. We can't use 18 because that never actually got produced, because you'd run out of iodine before that got produced. And we can't really use the 1.2 to do any stoichiometry with, because it's not all used, right? The mole ratio from the chemical equation doesn't apply to the amount of aluminum, because not all of it goes through the reaction. So if we want to use those mole ratios from the chemical equation, we can use either one of the numbers that are related directly to how much is used in the chemical reaction. The 2.4 grams of iodine that is actually used up, or the 2.57 grams of aluminum iodide that is actually produced. Either one of those you can start with. Let us start with the 2.4 grams of iodine, but you could do the same calculation from the amount of product. What we want to do is we want to find out how much of the aluminum is used. So if we're reacting 2.4 grams of iodine, we essentially just have to turn it into moles of aluminum and then mass of aluminum. So we can do that by first converting to moles. Then we are using the mole ratio from the reaction itself, because remember we have, let me write this up here, we have aluminum reacting with iodine, and it is forming our aluminum iodide. And to balance this, we can put a 3 there, and a 2 there, and a 2 there. So 2 aluminums react with 3 iodine molecules to form 2 aluminum iodide formula units. And so this is a 2 to 3 ratio. And so this is where we're getting this. We're saying that there are 2 moles of aluminum produced for every 3 moles of iodine that go through with the reaction. We know this amount of iodine, right? And so what we're going to do is we're going to turn it into the amount of aluminum that's actually used in the reaction. Then we can take it away from the amount that we started with, and we'll have how much is left over. So we convert to moles of aluminum, and then we're going to be working in masses. So our last conversion factor is going to convert us to mass of aluminum. So this is how much actually went through the reaction. We started with 1.2. We used some of it, but it's excess, so we didn't use all of it. So this is where we're finding out how much extra is left over. We used 0.170 grams of aluminum, and we got that again by using the grams of iodine and converting over to amount of aluminum used. If we look at the chemical equation, let me clear this up a little bit here. We have, we know how much iodine we used because it was the limiting reactant, 2.4. We need to convert 2 moles, and then we can go from moles of iodine to moles of aluminum. So that's what this is doing here. And then we want to convert to mass because we want to do our calculation in grams. So we have found out that there is 0.710 grams of aluminum actually used. We started with 1.2. We used 0.71. So it's just a matter of doing a quick subtraction there. We start with 0.20 grams of aluminum. We used 0.70 grams of aluminum, so there must be 1.03 grams of aluminum left over.